Hey folks, welcome to your second set of Chemistry 2 video notes. Today we're going to cover Chapter 2 from your textbook, The Numerical Side of Chemistry. Chapter 2 covers the following 10 topics: the difference between precision and accuracy, uncertainty in measurements and why some digits are considered significant, how to tell whether a zero is significant or not, how to write numbers in scientific notation to better show how many figures are significant, how to do math with sig figs and scientific notation, the basics behind the different units of measure, density and why it's useful, unit analysis, also known as dimensional analysis, which allows us to convert from one unit to another, how to use algebra to rearrange equations, and how we quantify energy. That's a lot to get through, so we better get started. All numerical quantities are either an exact number or a measurement. An exact number is universally defined and has absolutely no uncertainty. Things like there are 12 eggs in a dozen, or 2.54 centimeters in 1 inch, are considered to be exact numbers. Measurements, on the other hand, always have a certain level of uncertainty. All measured numbers should also be accompanied by a unit so you know what the number is talking about. As you may have learned from Lab 1, precision refers to how close a series of measurements are to one another, while accuracy refers to how close your measurements are to the true value. You can talk about the accuracy of any one measurement or a set of measurements, but in order to talk about precision, you must have multiple measurements to compare to each other. In these illustrations here, we had two teams, Team A and Team B, that both measured the diameter of the same coin. You can see that Team A's measurements were quite far from each other, making them imprecise. The average of their measurements were very close to the true value, so as a group they'd be considered accurate. Team B, however, got all the same exact measurements, making them very precise, but they were all pretty far away from the true value, making them inaccurate. Both teams measured the same coin with the same type of ruler, so why would there be a difference? Perhaps some members on Team A weren't measuring the true diameter of the coin, and maybe some members on Team B were convinced by another member to write down the same answer that they got, making them very precise. There's always a certain amount of error involved in taking measurements, whether that error comes from the device itself or the technique used by the person doing the measuring. Ideally, scientists would prefer measurements that look like this, where they are both precise and accurate. If our experiment can be repeated and show the same result multiple times, and those results are correct, that is golden. As I said, all measurements come with a certain degree of uncertainty. Take these two rulers, for example. The first one only goes by centimeters, so when you measure this coin, you can only say with 100% certainty that it's at least 2 centimeters. Anything past that is a guess. You can clearly see that it's somewhere between 2 and 3 centimeters though, so you might guess it's somewhere about 2.5. The other ruler goes by millimeters, so you can say for sure that it's 2.5 centimeters, but it looks to be right on the 2.5, so you might guess that it's exactly 2.50 centimeters. So anytime you measure something in science, you're supposed to measure what you absolutely know and then estimate the next digit down to the right. This is the agreed upon convention for showing the level of uncertainty for our measuring devices. The last digit we write down is our best guess at that level. We assume then that that last digit could be plus or minus 1. So looking back at our measurement from the first ruler, we can say that that coin is certainly between 2.4 and 2.6 centimeters. With the second ruler, we can say with certainty that the coin is between 2.49 centimeters and 2.51 centimeters. Only the digits that show the accuracy of a measuring device are considered significant. Which brings us to significant figures. In case you've forgotten the rules from last year, here they are. Any digit that is not 0 is automatically significant. Any leading zeros, or zeros that come before the first non-zero, are not significant because they're just placeholders. Trailing zeros, or zeros that come after the last non-zero, are significant if they're at the end of a decimal, This shows us that we're able to measure clear down to that decimal place. So those zeros are significant. Whole numbers are a little trickier though. It's hard to tell whether the zeros at the end of a whole number are significant. Like 103,000. Maybe I measured the 103 part, but the rest is just there as a placeholder. Maybe I measured all the way down to the ones place, so those 3 zeros are speaking to the accuracy of the measuring device. The way to show this looks unusual, but if you want those trailing zeros to be significant, trap them in with a decimal at the end of the number. Do not put another 0 to the right of that decimal, unless you actually did measure down to the tenths place. Lastly, any zeros that are trapped between 2 non-zero digits are significant. Sometimes the best way to show how many significant figures we have is to eliminate the leading zeros, or in a whole number, the trailing zeros. To do this, we write our number in scientific notation. What if my 103,000 was measured to the hundreds place? There's no way to show that that first 0 after the 3 is significant, unless I put it into scientific notation. To take a number from the decimal form to scientific notation, you simply move the decimal over until there's only one non-zero digit to the left of it. Write that number down with as many significant digits as you need, then write times 10 to the however many places you had to move the decimal. If you had a large number and had to move the decimal to the left, your exponent should be positive, and if you had a small number and had to move the decimal to the right, your exponent should be negative. To go from scientific notation to the decimal form, you just have to do the opposite. If you have a positive exponent, you move the decimal to the right, making the number bigger, and then fill in the empty spaces with zeros. If you have a negative exponent, you move the decimal to the left and do the same thing. So by this point, you hopefully understand the importance of significant figures, right? They show you how certain our measurements are. Well, what if we had to do math with our measurements, as we often do? There are 2 easy rules to follow when doing math with significant figures. When multiplying or dividing a measurement, your answer cannot have more significant figures than the measurement with the least sig figs. You'd perform your calculation, then count how many sig figs you need from the first digit. Once you've hit the allotted amount of sig figs, cut your number off there and round up or down based on the next digit. If you're adding or subtracting, your answer can't have any more decimal places than the measurement with the least amount of decimal places. Instead of counting sig figs this time, you're just counting how many decimal places you need, cut it off there, and then round. Remember, exact numbers, like conversion factors or counted numbers, do not play a role in the uncertainty. You only need to worry about sig figs and decimals with the measurements you're performing calculations on. Also, if your calculation involves multiple steps, do not round after each step. Wait until the very end and round based on how you should have rounded if you did each step. Let's do a few quick examples of how to report your calculated measurement correctly. Alright, so to show you how to appropriately report our answers to the correct number of sig figs when multiplying or dividing some measurements, here are a few examples. So if we have 2.0 times 2, obviously the answer is 4. 2 times 2 is 4, and 2 times 8 is 16. Now here we go though. This only has one significant figure. Remember, when we're multiplying or dividing, we're focused on how many sig figs our measurements have. 2.0 though has 2 sig figs. So we have to report our answer to the least amount of sig figs in our measurements, and that would be 1. So 4 is a totally fine answer, except you also got to put the units. So centimeters times centimeters is centimeters squared. For 2.0 times 2.0, both of these have 2 significant figures. So our answer has to also have 2 significant figures. We just put a 0.0 at the end of that because both of these then are significant. Remember, trailing zeros at the end of a decimal are significant because they tell us that we measured all the way down to that level of accuracy. So again, don't forget your units, centimeters squared. Now for 2 times 8, that's 16. 2.0 has 2 sig figs, but 8 only has 1. So this one's a little trickier. We can only report our answer to 1 sig fig. That'd be the 1 right there. So we've got to cut this answer off and then round up or down based on the next digit, and 6 would go up. So our answer then would have to be 20 centimeters squared. This 2 is significant, but remember trailing zeros at the end of a whole number are not significant. So this 0 does not count. It's not significant. 16 is a lot different than 20, so that may seem really weird to you. But hey, it's science. Everything's a little bit weird. Just remember, you have to go with the least amount of sig figs when you're multiplying or dividing. And if you end up with an answer like this, that's how it goes. All right, so in our next problem, we have 3 measurements that we're adding together. Remember, when we're adding or subtracting, we'll report our answer to the least number of decimal places as that of our least number of decimal place measurements. So 123 does not have a decimal place. This one has 3 decimal places, and this one only has 1. So when we add these up, we get 126.606. And remember, this guy did not have any decimals, so our answer can't have any decimals. So we'd cut it off here and round it. That would round up to 127 centimeters. Now, what if this were 123.0? Same deal. Our answer would be 126.606, but this time the measurement with the least amount of decimals are both of these. They both have 1 decimal place. So we'd cut it off here after the first decimal, and that doesn't round up. It stays the same, so it would be 126.6 centimeters. If it helps you think about it, imagine each of these are a ruler, and some of them have more lines on the ruler than others, and you can measure a lot more accurately with them. If this 123 without the point 0 is our least accurate of our measuring devices, whatever decimals we have on the other 2 don't really matter, because this could be plus or minus 1 from there. So the answer we put has to indicate that we could be plus or minus 1 from there, because our least accurate measuring device could also be plus or minus 1.
As for scientific notation, I'm not going to make you run those calculations by hand. You're welcome. But here's how you'd punch it into a calculator. You type in the main part of the number, the A part if you were paying attention to the setup on the last slide. Then you hit the double E button. For the calculators in our classroom, you have to hit the second button first, which is in the top left corner, and then hit the double E button. This will show up as just a single E on the calculator screen, and it represents the times 10 to the part of the notation. Lastly, type in your exponent. Now that we know how to properly show the uncertainty of a measurement, even after we perform calculations on it, we can talk about how to express what a measurement means. As I mentioned before, every measurement comes with a number and a unit. That unit helps us understand what the number is talking about. Since we tend to stick with the International System of Units in science, that's all we're going to talk about today. The base SI units include meters for length, kilograms for mass, seconds for time, Kelvin for temperature, moles for the amount of a substance, and amperes for electrical current. Using those units, we can come up with some more units known as derived units. These include the cubic meter, which equals 1,000 liters for volume, the Pascal, which equals a kilogram meter per second for pressure, the joule, which equals a kilogram meter squared per second for energy, and the coulomb, which equals amperes times seconds for electrical charge. Any one of these units can be expressed in very small quantities or very large quantities if we add a Greek prefix before them. For example, milli means 1,000th, so 1,000 millimeters is equal to 1 meter. A kilo means 1,000, so 1 kilometer is 1,000 meters. Familiarize yourself with the Greek prefixes here. You may have to memorize them. On the topic of measurements, you may have thought that degrees Celsius was the SI unit for temperature, and understandably so. However, because of the way a lot of our scientific equations work out, we often use the Kelvin temperature scale a lot more frequently than the Celsius temperature scale. To convert between Kelvin, Celsius, and Fahrenheit, you could use a combination of these 3 equations. Let's do a couple examples of converting between different degree scales.
All right, remember our 3 equations we can use to convert temperatures. We'll go ahead and do Celsius to Fahrenheit first. So if we want to know the degrees Fahrenheit if we're given Celsius, we take 9/5 times our Celsius degree
plus 32. So in this case, that'd be 9/5 times 30, which is 54. And then we add 32. That would give us 86 degrees Fahrenheit. If we want to check our work, we can do that backwards and plug that into the degrees Celsius equation, which is 5/9 times our degrees Fahrenheit minus 32. So if we take our 86 minus 32, that's 54, and then times 5/9 is back to 30. Lastly, if you're going from Celsius to Kelvin, that's just plus 273.15. So 273.15 plus our 30 degrees Celsius. So we'll go to 303.15 Kelvin. If you had Kelvin and you wanted to go to Celsius, you would just subtract 273.15.
Density is an extremely useful physical property. It measures the compactness of matter. In other words, it tells you how much matter there is in a certain amount of volume. It follows the equation above, where D is density and is often measured in grams per milliliter or grams per cubic centimeter. M is mass measured in grams, and V is volume measured in milliliters or cubic centimeters. Since density is an intensive property, one which does not change based on how large or small your sample size is, it can prove very useful in comparing different substances and identifying them. Mass and volume are both extensive properties, as they depend on the size of the sample. Say I had a cube of metal that looked like gold. If I wanted to know if it was gold or just lead painted to look like gold, I could find the cube's mass, then find the cube's volume, divide the two, and compare my answer to a chart of densities of metals. What if I didn't have a cube, but just an odd-shaped chunk? You can easily find the volume of any object, regardless of its shape, by incorporating the Archimedes principle. If you place the object in a container of water, it'll displace the water. Much like when you get into a bathtub, the water will rise. If you can measure how much of the water was displaced, that volume is the same as the volume of the object that's causing the water to be displaced. Normally, I'd do a couple examples here, but these notes are already going to run long, and you've done this for a few years now, so I'm going to trust you to figure it out. If you have questions about the density equation, though, please ask. Now, on to everyone's favorite, unit analysis. Unit analysis, also known as dimensional analysis, helps us convert our measurements from one unit to another. Here are 3 very short steps to unit analysis. Step 1, write down the measurement and unit that you're given, and then identify what units you're trying to convert to. Step 2, multiply that measurement by a conversion factor so that the original unit of the measurement cancels out. To cancel out units, you have to have the same unit on top as well as on bottom. If you can't get to where you're trying to go with just one conversion factor, multiply by as many conversion factors as you need. Lastly, step 3, perform the calculation by multiplying all of the top numbers and then dividing by each of the bottom numbers. Make sure you land at the correct unit when you're done. Let's do a quick example of this.
All right, so let's say I had a cube of lead, which has a density of 11.4 grams per milliliter. Remember, that could also be written as 11.4 grams equals 1 milliliter, and that is considered a conversion factor. If I take the mass of that cube and find out that my cube has 9.3 grams, I could go ahead and convert the grams to milliliters using dimensional analysis. So I start with the number I'm given with the unit, then I multiply by a conversion factor, in this case 11.4 grams for 1 milliliter, and multiply the tops, divide by the bottoms. First, make sure your units cancel out, so I've got grams on top and grams on bottom, and I'm left with milliliters, so that's good. If I take 9.3 divided by 11.4, I get 0.815789, or somewhere around there. Now remember, we got to go with the number of sig figs in our measurement. 9.3 is the only measurement we have here. So we got to count from the first non-zero digit to the left, 8, and then 1 is 2 significant figures. So we're going to cut this off here and call it 0.82 milliliters. You should already know some algebra. In chemistry, we tend to stick with the very basics of algebraic manipulation. If you have an equation, but you want to solve for one of the variables, you'll need to multiply, divide, add, or subtract variables or constants to get that desired variable by itself. The important thing to remember is that whatever you do to one side of the equation, you have to do to the other. Let's take the density equation for example. If we knew the mass of something and its density, we could use unit analysis like we just did to figure out the volume. That's a totally acceptable way to do it. However, since we have a density equation, it might just be easier to solve for volume with that. You'll get the same result and essentially perform the same calculations either way, but algebraic manipulation might save you some steps in the long run. So, if your equation is d equals m over v, and we're trying to solve for v, you want to multiply both sides by volume first. This puts the volume up top, giving you density times volume equals mass. Next, we want to get rid of the density variable on the left side, so divide by density on both sides. This tells us that the volume is equal to the mass divided by the density. Feel free to plug those numbers in from our last example and see if you get the same answer. The last thing we'll talk about today, and something that's kind of a lot to put on one slide, is how we quantify energy. Energy is defined as the capacity for doing work. If something has a lot of energy, it can do a lot more work. A common unit of energy is the little c calorie, which is defined as how much energy it takes to heat up 1 gram, or about 20 drops of water, by 1 degree Celsius. 1,000 of those, or 1 kilocalorie, is equal to the big C calorie, which is the one we use for food. 1 little c calorie is also equal to 4.184 joules, the SI unit for energy, which is named after one of the scientists who discovered the law of conservation of energy. When energy is transferred from one object to another, we call that heat. And there's a special equation that goes with that. As we saw before, the little c calorie is how much energy it takes to heat up 1 gram of water by 1 degree Celsius. This is also known as water's specific heat. The specific heat of any substance is how much energy it takes to warm 1 gram of that substance 1 degree Celsius. And it plays a special role in our heat equation and is labeled as C. According to our heat equation, the amount of heat is equal to the mass of the substance times the specific heat of the substance times the change in temperature of the substance, which we can find by subtracting the final temperature by the initial temperature. We usually stick with joules, grams, and degrees Celsius for our units here. In a closed system like that of a bomb calorimeter, our total amount of energy does not change. A bomb calorimeter is an insulated system that includes a container or a bomb in which you can ignite a particular substance, surrounded by a known amount of water at a certain temperature. As that substance burns, it releases energy. Since the system is closed, the energy doesn't just go away, it gets absorbed into the water, causing the water to warm up. If we know the mass of the water, the temperature change of the water, and the specific heat of the water, we can calculate the amount of energy that the water absorbed from the substance when it was burned. This energy change, or heat, is exactly as much energy as the substance gave off. This is actually how we determine how many calories are in a particular food. We're not going to go too crazy with the heat equation here, but you do need to memorize it and know how to use it. One important thing to remember is to make sure that your units cancel out. If you're given a specific heat in joules per gram degree Celsius, your mass needs to be in grams and your temperature needs to be in degrees Celsius. Let's do an example of this. All right, so let's say I wanted to know how many calories, like food calories, were in a Twinkie. And I put that Twinkie inside of a bomb calorimeter. The bomb calorimeter had a mass of water of 1.00 times 10 to the 4th grams, which is the same as like 10,000 grams. But remember our scientific notation, this is 3 sig figs, but that's only 1. So in order to show that that number is 3 significant figures, we had to put it into scientific notation. Next, our specific heat of the water, if you'll remember, is 1.000 little c calories per gram degree Celsius. And I measured the temperature of my water before and after I burned that Twinkie. My initial temperature was 25.0 degrees Celsius, and my final temperature was 45.0 degrees Celsius. So now all I have to do to find the energy that the Twinkie released is figure out how much energy the water absorbed. To do that, I just plug this into my heat equation. So the heat absorbed by the water is equal to the mass, which was 10,000 grams. But for mathematical purposes later, don't forget that that is 3 sig figs there. And then times our 1.000 little c calories per gram degree Celsius. And then times our change in temperature, which would be 45.0 minus 25.0. And if we round to the right decimal places, we should get 20.0 degrees Celsius. So now I've got 3 sig figs here, 3 sig figs there. When I run that through the calculator, I have 10,000 times 20, which is 200,000 little c calories. If you need to double check your work as you do it, just make sure your units cancel. So grams is on top and bottom, and degrees Celsius is on top and bottom. So you're left with little c calories, and this is what you get. Since it's 3 sig figs, we do have to report it like that, so it'd be 2.00 times 10 to the 1, 2, 3, 4, 5, 10 to the 5 little c calorie. And then remember, we're looking for the amount of food calories that Twinkie has. So we could take our 200,000 little c calories and convert it to big C calories. 1 big C calorie is equal to 1,000 little c calories. So if we take 200,000 divided by 1,000, we get that Twinkie would cost you 200 of your food calories for the day.
Well, that's all for today, folks. I know that was a lot to cover, and these notes are probably longer than you'd prefer, but I hope it helps. This is one chapter that I am going to ask you to take the time to actually read. The book does a very good job at explaining some of these concepts, and as you read, you can work out some of the practice problems to help make sure you understand what's going on. As always, if you have any questions, let me know.